Welcome to the second presentation in Unit 4 entitled Solids, Liquids, and Solution. The learning goals for this particular presentation are that you be able to distinguish between the states of matter based on intermolecular forces, and that you be able to relate those forces to entropy and enthalpy in a solution. And finally, that you be able to understand how concentration will relate to colligative properties. So, the first thing is we want to look at the condensed phases of matter. Okay, the two condensed phases of matter are considered to be solids and liquids, and the reason why they're considered to be condensed phases of matter is because they have a very, very high density. The density is really high because the molecules are stuck together. They're pretty much as close to each other as they can get. Because they have a condensed phase with a high density, these things are said to be incompressible. Okay, you can't take a liquid and squeeze it together. Okay, you can't apply pressure here and have the molecules fit together better. So the proximity of the molecules make the intermolecular forces significant. So when you look at this thing, you can say, okay, in the solid phase, these two molecules are very close to one another, and because of that, there is an intermolecular attraction between the two. So the condensed phases tend to have the greatest intermolecular forces. So in terms of states of matter, what we're referring to is solids, liquids, and gases. Okay, there are exotic forms of matter that we're going to really study in this particular class, but there are things like photonic matter and quantum spin liquids and things like that. But for now, we're going to stick with solids, liquids, and gases. Now, the interesting thing about solids is a lot of people see them as stationary atoms, and they're not. They can actually not really rotate very well, but they can vibrate. They can rotate along a bond. So if you have these two things right here, let's say we have molecules right here. This molecule can rotate relative to this one, but it's got to be locked in place as far as translation. Okay, so these two things can vibrate relative to one another. This one can move this way and this one can move this way, but then they move right back. There is no translation. Okay, in other words, you can't take this thing in a solid and have this molecule move here and this molecule move here. They can vibrate back and forth, but they can't translate. Liquids can rotate, vibrate, and translate. Gases can rotate, vibrate, and translate as well. So the molecular motion is similar in a gas and a liquid, whereas in a solid it's considered to be kind of locked in place. So when we look at the intermolecular forces in chemical bonds, an intermolecular force requires less energy to break than any bond. Okay, it is not considered to be a bond because it requires less energy. So if you were to look right here, when you have these water molecules have this intermolecular attraction right here. This is a dipole moment. Okay, you have a partial negative and you have a partial positive, and because of that, they're attracted to one another. This right here, breaking the intermolecular forces for this to go from a solid to a liquid only requires 6.02 kilojoules per mole. Okay, it only requires 40.7 kilojoules per mole to go from water into steam. Okay, it requires 935 kilojoules to actually break this bond. That's why whenever you add heat to a particular system, it's not like you're going to suddenly produce hydrogen gas. All the energy is going into breaking the intermolecular attractions because they're so much lower. Now, the reason why the energy required to go from a liquid to a gas is much higher is because here, going from a solid to a liquid, all you're doing is kind of breaking this but allowing them to reform. Okay, it's just making it so they're no longer rigid, but those intermolecular attractions are still there. Whenever you go into the gas phase, you severely reduce the intermolecular attractions to about zero. So let's review the intermolecular forces. The first one you have is called an ion-dipole interaction, and that's what happens whenever you have an ion, either a positive or a negative ion, cation or anion, whenever it interacts with a polar molecule. Okay, this is considered to be a strong attraction because you have a full partial, or you have a full charge interacting with a partial charge. So because of that, this is a very strong attraction because of Coulomb's law. Okay, the higher the charge, the greater the attractive force. So since I have a very high charge right there, I'm considered to have a strong attraction. The second one is called a dipole-dipole interaction. This is also generally considered to be relatively strong. It's not nearly as strong as our ion-dipole interaction, but we have partial positives and partial negatives. Because of that, Coulomb's law says you're going to have an attraction, but it's going to be not as strong because both sides have partial charges. Next, we have what are called the London dispersion forces, and the London dispersion forces are because electrons are always moving. You can't look at the electron as a static thing. You can never identify the position that an electron is in. Instead, it's always moving. Because it's always moving, there is a temporary uneven distribution of the molecules, or excuse me, of the electrons, and because of that, it will create partial positives and partial negatives. But that is an instantaneous, very quick, and then it goes away. It's temporary. Because of that, this is considered to be a very weak attraction. Now, London dispersion forces. Okay, London dispersion forces, if we continue this, skinny molecules are more polarizable. The reason being, you can actually create a partial positive charge here, and the partial negative charge can go all the way over there. It's a lot more satisfied than if you had a partial negative and a partial positive here. If you had this situation, they would attract. It can easily move back and forth from one to the other. But if you have a partial positive over here and a partial negative over here, that's more likely to create what we call a polarizable cloud, because the cloud is bigger, it's more spread out. The larger an electron cloud, the more polarizable it is. And if you think about that, that makes kind of sense. If you have the nucleus right here, and you have a negative charge there, and you have a negative charge here, the uneven distribution, because I have so much more space to work in, there's more likely to be an uneven distribution of charge here, because the electron can be here, 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 and here, and they're still relatively stable because they're still spread out. If you were to put those same electrons in this little confined area right here, they're very close together and are going to repel each other very quickly. So because of that, the larger the electron cloud and the more skinny the molecule is, as skinny as opposed to like this, the more polarizable the molecule is. So what matters more? So far we've gone on the assumption that the dipole-dipole interaction is always going to be more. And for the most part in AP chemistry examples it is. Polarity and intermolecular forces dominate when the molecules have similar size and similar shape. Okay, if you have something that is roughly the same, which tends to be what we deal with if we're comparing like HCl to HF, those right there are considered to be of similar size and similar shape. If you have something that is dramatically different, okay, something like, oh, I'm looking at water and I'm looking at C10H22O10, okay, those are dramatically different. Whenever you have something that's dramatically different, a lot of times the London dispersion forces tend to take over. So you have to look at it and say, okay, well, are intermolecular forces going to dominate, or are London dispersion forces going to dominate? Now, one real quick thing as a review, hydrogen bonding is a special type of dipole-dipole interaction. Okay, remember this is a dipole-dipole, but what's really important about the dipole-dipole interaction is that this is an unusually strong attraction. The reason why is hydrogen is relatively easy to form an attraction with. It almost always becomes partially positive. These three things right here are the most electronegative. They have a very, very high electronegativity, and they're very, very small. Okay, they're in that second period where they only have 2 electron orbitals. So because of that, they produce something called hydrogen bonding. This exposes the proton of the hydrogen and actually makes a pretty strong attraction for things like water, which is what you see here, or if you have ammonia, which is right there. This strong attraction tends to make things liquids at room temperature as opposed to some of the other similar polar covalent compounds. So now this says rank the molecules below from the least to the greatest polarization. So now whenever you're looking at this, the first thing you need to look at is the electronegativity difference. Okay, you need to look at electronegativity. And so if we look at this, we can eliminate one as having the absolute least polarization, and that's going to be this one. This is going to be our 1 because it's our least polarizable because we have a non-polar bond right there. Now what we need to do is we need to look at the rest of these and say, okay, well, what else do we have going on? So this is completely nonpolar. This right here is also going to be nonpolar, and it's going to be nonpolar because of symmetry. So you could have, there is a definite electronegativity here, but overall the entire molecule is nonpolar. It is not as nonpolar as this, but it is still nonpolar. So we would call this 2. Now the next thing that we need to look at is we need to look at this right here. Okay, when you look at this particular substance right here, you have to decide what's going on as far as these. Hydrogen and carbon have roughly the same electronegativity. I think one's 2.1 and one's 2.5. So they're very, very, very close. So you have to decide if an oxygen interacting with a hydrogen or an oxygen interacting with a carbon is going to produce the greatest electronegativity difference. And it turns out that this one is going to be number 3, and this one is going to be the most polarizable. The reason why is it has 2 very electronegative oxygens, and they're not opposed to one another. They're kind of pulling in the same direction. One's pulling up and one's pulling kind of down into the right, but there's going to be a net polarity right here that's going to pull this thing right here. It's going to be a very, very, very polar negative charge, which means this is going to have a very, very, very negative or partial positive charge. Next, it says rank the molecules below from least to greatest polarization. So if you were to look at it in this particular case, we got a little cut off of the picture there. These are very similar molecules. They're all considered to be nonpolar. So because of that, I know it's not going to be dipole-dipole interactions or ion-dipole interactions or anything like that that's going to take over. Instead, this is going to be London dispersion forces, because we're talking about the polarizability of the cloud at this point. So you're looking at the size. Now, fluorine is the smallest of the halogens. Okay, so since it's the smallest of the halogens, it has a relatively small size. It is going to be the least polarizable. So we're going to say this is 1. Iodine, on the other hand, has the largest molecules. And because it has the largest molecules, it's going to produce the largest electron cloud. As a result, it's going to have a 4. So this is going to be our most polarizable. And you can fill in the rest. It would go fluorine, chlorine, bromine, iodine, based on the size of the electron cloud. Now, we need to look at some things as far as where these intermolecular forces come into play. The first one is called surface tension. And you can see this is actually a water strider. It's actually walking on water. And you can see the indentations of the bug's feet, I guess they call feet, into the water, where it's not actually stepping into the water, it's actually walking on water. Now, the reason why he's able to walk on water is because water has something that's called a surface tension. If you think of the top layer of water, and there's these water molecules right here, you have this intermolecular attraction right there. So there's this intermolecular attraction where they don't want to move. Now, whenever I put my foot down, it can actually break that intermolecular attraction, but only if it has enough force to move these molecules away from one another. So there's a definite attraction, and water has a pretty high surface tension. So this is the tendency of a liquid to resist an outside force, and it's because of intermolecular forces. So this right here is dependent on intermolecular forces. If you have something that's like oil, oil is going to have a lot lower surface tension because the resistance to shear stress or the breaking of intermolecular forces. And you can think of it as this. It's sometimes the resistance to flow. So how easily does a liquid flow? Does it pour very easily? The reason why it pours very easily is it has low intermolecular attractions. The greater the intermolecular attractions when something pours, these things actually stick together. And the reason why they're sticking together is there's such a strong attraction between the partial positives and partial negatives. Okay, all liquids are generally compared to the viscosity of water. There are some things like syrup that syrup has a very high viscosity. And then you have things like oil, which have a very low viscosity. So those sort of things are, vegetable oil has a very low viscosity. And so because of those, this resistance to flow is based on the intermolecular attractions between molecules. Next, we have what's called a phase change. And you should be familiar with a phase change already, but if we were to look at it on an intermolecular forces basis, we have water, and then you have another water molecule. And what you have is you're adding energy to a system, and the energy is not going to making these things move faster, but the energy has to go somewhere. And what it's doing is it's breaking this intermolecular attraction. When you break that intermolecular attraction, you're changing the temperature that's required, or you're breaking and changing the phase, going from solid to liquid or liquid to gas. Now, if you were to insert something like sodium chloride into the solution, if you add salt to a water solution and make it a saltwater solution, at that point the boiling temperature actually increases. The reason why is you have a full positive charge that is now a greater attraction than you had when you had the partial positive charge. So this attraction right here, this intermolecular force between the sodium and the oxygen, is greater. It's a stronger attraction than you had previously. If you have a stronger attraction, that's the attraction you have to break in order to change the phase. So whenever you add something like that, you're increasing the intermolecular forces and therefore changing the phase change temperature. Next, you have something called vapor pressure. Liquid and gas are generally considered to be in equilibrium, which means that even though you have something that's a liquid, there are some gas molecules that are above it. Because remember, the liquid or the gas phase is just the ability to escape gravity. So you have free movement where some particle randomly has enough energy where it can escape the liquid. When it can escape the liquid, there are going to be some gas molecules here. So that's what we're talking about when we talk about vapor pressure. Now, the vapor pressure, as you increase the intermolecular forces, you actually decrease the number of gas molecules, because once again, the amount of energy required to escape gravity, you have to break that intermolecular attraction. So even at low temperatures, you're going to have some liquid escape to the gas phase, but most of the time it's not going to be very much. Now, the higher the temperature gets, the more molecules are going to go into the gas phase. Now, it says Boltzmann distribution, and the reason why is it's a random occurrence due to chance that you're going to have these molecules go into the gas phase. So you have to look at it on a statistical basis, and that's why it says Boltzmann distribution. So we have what are called phase diagrams. Phase changes actually depend on both temperature and pressure. And if you think about that, that makes a lot of sense because pressure will help determine intermolecular forces as well. If I have a container and I've got molecules in here and I squeeze that container together, I'm going to bring the molecules closer together. So a lot of times you'll see what are called phase diagrams, and these are sometimes called triple point diagrams. Okay, the reason why they're called triple point diagrams is you have this right here. This right here is called the triple point. And what it is it's the one point where you have an equal amount of water, liquid, vapor, gas, and solid, ice. So you have solid, liquid, and gas all at the same time in the same test tube, and it's not like it's freezing or it's melting and it just happens to be there for a second. It's a continuous equilibrium position between solid, liquid, and water. So you would write it something like this, where you have solid, liquid, and then gas, and they're all in equilibrium with one another. So you see the triple point of water. The triple point of water is 273.16 K, which is roughly pretty close to 0 Celsius. So that's pretty close to the freezing point of water. But then if you notice, the distinct difference is it's almost at a perfect vacuum. Okay, so you have something that is very, very, very low pressure and then a relatively reasonable temperature. Okay, whenever we look at solids, there are two classifications that we look at for solids. We talk about crystalline solids and amorphous solids. Crystalline solids tend to be like what you see with crystals. That's why it's called that, where you have a regular pattern of cations and anions generally. In other words, you have the structure that has been set to minimize repulsions. Okay, you have this structure that's set to minimize repulsions. The smallest unit of a crystal is usually called a unit cell crystal. So for example, this thing right here would be a unit cell crystal. If I had a copper, sulfates, a sulfur, 4 oxygens, and then you have the water crystals around it. So this right here represents a unit cell crystal because it's the smallest possible structure of a crystal. Whenever we talk about metallic bonds are what we talked about in first-year chemistry as a diffuse sea of electrons. Basically, with metallic bonds, everything is a cation, and you don't have a sharing of electrons. What you have is these electrons right here are free to move. And so this is whenever you have something like gold or platinum bonded with gold or platinum. It's called a metallic bond. And like I said, these electrons aren't shared. They're free to move between each other. The attraction of a metallic bond is stronger than van der Waals. Okay, so whenever you have the attraction, it's going to be much greater than you have for, say, a covalent compound. So now if we revisit solutions, we know that solutions is basically taking something and dissolving it in something else. For solutions to form, remember we say in chemistry, things don't happen unless there's some sort of energy benefit. So there's got to be an energy decrease. That's the reason why things happen in chemistry. There's a couple of things though with a solution. Sometimes it will lower the energy, but almost always it will increase the entropy. So it's actually the combination of these two, not just the decrease in energy, but it can either increase entropy or decrease energy or both. So entropy is generally defined. Most people commonly say that it's the disorder of a system. That's not a great way of trying to say it. Another way of trying to say it is it's the number of ways that a system can be arranged. So for example, if I have a container connected to another container, and I have 3 molecules in it, there's a number of ways that I can arrange the system. I can put all 3 molecules in the left box. I can put all 3 molecules in the right box. I can put one molecule in the left and 2 in the right, and I can put 2 on the left and 1 on the right. So we can quantify this idea of entropy, and we can say how many number of ways can the system be arranged. Now, since we're talking about atoms, the number of ways that a system can be arranged is huge. So we're not going to actually count the number of ways that a system can be arranged, but we can express these things in terms of entropy. Now, one thing that you should understand is that systems will always seek to maximize their entropy. You're never going to have a mixture of molecules where all the red ones go to the bottom and all the blue ones go to the top if they can help it. Okay, if there's any sort of energetic benefit, maybe it does it, but they always seek to maximize the number of ways they can arrange themselves. So now we need to talk about the enthalpy. Now remember, if we talk about from earlier this year, enthalpy is basically referencing heat on a per mole basis, is the basics of it. So whenever you break a solute-solute bond, so if you have a NaCl bond, whenever you break that attraction, it's considered to be a solute-solute bond. So whenever you break that attraction, it's an endothermic reaction because it requires energy to break that attraction. Okay, whenever you look at it from the breaking the solvent-solvent bond, if you have an H2O and an H2O, you need to break that intermolecular attraction. Whenever you break that intermolecular attraction, it's also endothermic. So it requires energy at this point to break the solute-solute and solvent-solvent interactions. So in order for this to be an energetically beneficial reaction, you actually have to form new attractions. So now I have an attraction between the sodium and the oxygen and the chlorine and the hydrogen for my example. It's only through that, the formation of these new bonds, which is an exothermic reaction because you're saving energy or you're releasing energy by storing it in bonds, that actually makes sense for a solution to form. Okay, there's a couple of things you need to know. Saturation. Saturation is the most amount of solute that a solvent can have, and it does depend on pressure, and it depends on the solute as well. Whenever you have something that's unsaturated, it can hold more solute. Whenever something is saturated, it's at the maximum. And whether something is super saturated, it's holding more than the normal amount. And generally, whenever you see this, you can start to lower the temperature and it'll form crystals. Okay, one important thing whenever you're developing solute or solutions is that like dissolves like. So for polar molecules, the dipole-dipole interaction dominates, and therefore polar solutes want polar solvents. So that's why you tend to see things like sodium chloride will dissolve in water, but it doesn't necessarily dissolve in oil. For nonpolar molecules, the London dispersion forces dominate, and so nonpolar substances will bond with nonpolar solvents. Whenever you're trying to increase the solubility of a solid, there's a couple of different ways that you can do that. The first one is you can increase the temperature. Whenever you increase the temperature, you're actually increasing the energy of the initial energy that a substance has, and so it makes it easier for you to break the solute-solute and solute-solvent interactions. So whenever you do that, you're breaking this interaction and you're allowing the solute to now form with a solvent as opposed to the solute. Okay, so you're decreasing the energy required to break that. So increasing the you can also it also decreases the energy of breaking the solvent-solvent. Whenever you want to increase the solubility of a gas, you actually have to decrease the temperature, and you need to decrease the energy of agitation so you can't shake it up, and you can also increase the pressure. Because remember, at this point, whenever you're trying to increase the solubility of gases, these things already have enough energy so that they can escape the liquid. And if you give it even more energy, you're giving it more energy, you're making it more likely that it's going to escape the liquid because it has more velocity. It's going to achieve that escape velocity. So there's a couple of different ways where we talk about concentration. You should be familiar with almost all of these by now, but mass percent is the mass of the solute divided by the mass of the solvent times 100. Okay, the mole fraction is moles of A divided by the total moles of the solution. Now that does include A. So since A is part of the solution, you have molarity, which is the moles of A divided by the liters of the solvent. You should be familiar with molarity. You should be familiar with molality. One thing that you may not be as familiar with is parts per million or parts per billion. And that's where you just take the mass of A divided by the total mass and then multiply it by a million or a billion. Okay, if you multiply it by a million, you're going to get parts per million. If you multiply it by a billion, you're going to get parts per billion. Okay, colligative properties. are the ones that depend on the ratio to the solute solvents. So if I have 1 sodium chloride and 5 H2O molecules, this ratio of solute to solvent particles will actually determine these colligative properties. That's what colligative properties means. Colligative properties include vapor pressure, boiling point, freezing point, and osmotic pressure. And osmotic pressure is just how likely something is to fit between these gaps. Okay, boiling point, we said solutes effect. The intermolecular forces are different. If the intermolecular forces are different, then the boiling point is elevated. Freezing point, we're going to depress the freezing point at this point because we're increasing the attraction between the two, so we're going to make it more likely that these particular bonds are going to form. Vapor pressure we've already talked about. We've said that as a molecule escapes, it is less likely to occur if the intermolecular attractions are great, or more likely to occur if the intermolecular attractions are small. And finally, we have something that's called a colloidal suspension. This just comes up because it's kind of we're trying to fit it in somewhere. You have a solution, which is generally where solutes are dissolved into a solvent. A colloidal suspension is a little bit different. This is what happens if you ever have to get a medicine and you have to shake it up. A colloidal suspension is not a solution. The reason why it's not a solution is because they have larger particle sizes. So instead of the particles being able to kind of dissolve in the water, they're really, really, really big. And so this actually represents two distinct states of matter. Instead of it being an aqueous solution, you have a solid and then you have a liquid around it, as opposed to what we have whenever we have a solution. A solution has our sodiums, and then it's surrounded by our waters. So it represents an aqueous state because it's taking the substance and it's surrounding it with water, as opposed to just being two distinct different states.